Greetings. We're looking at gravitational potential energy, not the most difficult concept we're going to cover in this class, but like anything, depends on how you look at it, and actually in a very large sense, not that it's crucial for us right now, it actually is more complicated than just this, but as long as we are on the Earth's surface and reasonably, under the height of the tallest mountain, or this formula actually works just fine. It's actually a more broader way to look at it, but it's not the scope currently of this class. It will be in Physics 2. So, first of all, you'll oftentimes see me write this a few different ways. I may write it as simple as gravitational potential energy is mgh. That really isn't as complete a statement as what you see circled here, for reasons that we'll talk, but I will oftentimes in haste write that. But this and this are important for a reason, and we'll discuss that in a second. But the bottom line is this. You compare two locations, a shelf and the floor, and if you put a heavy object, like a bowling ball, we'll say, up on top of the shelf, it will have gravitational potential energy more so than it does when it's on the ground. Likewise, if you put a ping pong ball up here, it'll have some gravitational potential energy, not as much, we'll write it smaller, and it will have more so than it does compared to when it's on the ground. And if we want, and we will oftentimes want to do this, we can call one of the two locations that we're comparing, the ground oftentimes, 0. We'll call that a height of 0 meters, or a y value of 0 meters. And sometimes that is just understood in the problem. Just, that's understood. And that's why you'll see this used, mgh, because if I use this, what I'm assuming is, hey, the problem is so obvious that the ground is 0, the height is that delta y. Whatever height you're at, we're comparing it to the ground, and it's straightforward. But it is more thorough to use this approach because, well, of the following. So if I said that you have a bowling ball here that's way up high, and it has a mass of, say, 5 kilograms, what would its gravitational potential energy be at that location if we assume that the ground is 0 meters and let's say the shelf is 2 meters tall. So our gravitational potential energy would be the mass, 5 kilograms, times g, 9.8, times 2 meters. Now, I could call it delta y, and delta y would be, hey, compared to the ground, if I started at the ground and I compared it to here, delta y would be 2 meters minus 0, which would just be 2 meters. Change in gravitational potential energy here means at this level I would have 0, and at this level I would have the final. So, but in this case, if we know we have 0 to begin with, we can just basically look at the final, if you like, quotes, potential energy. Compared to the ground, what's its potential energy? And that's going to be, well, 10, roughly. If we estimate this using 10, that's 50 times 2, that's 100. So it's 100 joules of gravitational potential energy. Great. Terrific. Here's where the delta y comes in. And by the way, that's about as hard as you're going to, that's, for the most part, that's what you're going to run across. But what if there was a basement? What if there was the floor and then there was a big gaping hole and there was a basement floor underneath, 3 meters below? Maybe call it negative 3 meters, right? Because if this is 0 meters, then I got to call that something else. Well, wait a second. What would the bowling ball have in terms of potential energy if it was here then? Now, one way to do this is to say, oh no, let's just reassign the basement as 0. You see how that's arbitrary? It doesn't really matter where you call 0. We could do that, but let's say we keep this as 0. Then it's possible to have a negative change in potential energy, or to be what we would call in a potential energy well, which makes sense because if you're in a well, you're below ground level. So that's kind of the reasoning behind that statement. So you could actually say that the change in potential energy in going from the ground to here, well, if I had 0 joules here, I would have, let's see, 3 times 10 is 30 times a 5 kilogram ball, that's 150. I would have negative 150 joules at that location. So this delta Y is important. I will oftentimes, and we don't run across this situation very often, but it is the reason that their formula looks so much more complicated than just, hey, potential energy, gravitational potential is mgh. So be aware of that. You can have this situation. It won't come up very often, but it is important to note. So what would be the change in potential energy from here to here? Now we really need to look. If we brought it from the basement up to the top of that shelf, now we have to really stick to, hey, delta U G equals mg delta Y, and say, all right, the change in gravitational potential energy is going to be the mass, 5 kilograms, times G, I'm going to just estimate it at 10, times the change in Y. So my final height was a positive 2, minus my initial height, which was negative 3 meters in the basement. And as you'll see, that comes out to be 5, right? Yeah, 5. So 5 times 5 is 25, times 10 is 250. So my change in potential energy from the basement to that floor is positive 250 joules. The only other thing I will mention about gravitational potential energy is this, and that is, it doesn't matter how you get to a certain height. So if you have the ground and you have a certain height above it, doesn't matter what it is, call it 2 meters, 3 meters, whatever. If you push an object up a ramp and get it to here, or if you use an elevator to take the object from here to here straight up, or if you, I can't think of another way. But regardless of how, or if it's, how about this, if it was an object on a pendulum, all right, and it was swinging and it got to that height, there you go. So this pendulum was swinging and it went from here to here. Regardless of how it got there, the change in potential energy from, we'll assume 0, to this is the same. How you get there doesn't matter. Once you get to this height, how you got there doesn't matter. It's just, that's the potential energy. So you'd be on the lookout for situations where you can say, well, gravitational potential energy for all of them is the same. It doesn't matter how they got there. You might run across, you can imagine, some multiple choice problems in particular that where they challenge, your understanding of that. The work you might do in, gravity or whatever else might do in getting them there could be different. Like here, the distance is longer. Well, the work actually is going to be the same. I lie. The work done getting them there would be the same, because this would be a large distance with less force. This would be a short distance with a larger force. So you end up with the same amount of work, assuming they were, starting at rest and ending at rest. So I'll be careful what I say. All right, so that's gravitational potential energy, and we'll talk about how it fits in with everything else in future videos.